Welcome to Next Gen Manufacturing Nexus. Today we're diving into a really tough question. How do you design the perfect material for something like a jet engine or a high-performance race car? We're talking about advanced composites. These things are unbelievably strong, super lightweight, but they're also notoriously difficult and expensive to get just right. So let's get into it.
Really think about that. For years, making a new material was basically just a whole lot of guesswork. You'd build prototypes, you'd run expensive tests, and you'd just hope for the best. But what if there was a smarter way? A way to find that perfect recipe without all the waste?
And that's really the heart of the problem, right? The old way of doing things was just painfully slow and inefficient. You mix up a batch, you test it, it cracks. You tweak the formula, and you try all over again. That whole cycle just burns through an insane amount of time, money, and materials. It's been a huge roadblock for innovation.
So this brings us to what we're calling the Composite Conundrum. How do you possibly optimize a super complex manufacturing process that has all these different variables without having to run hundreds of really expensive experiments? Well, it turns out engineers have come up with some pretty brilliant ways to do exactly that. This right here is the classic work smarter, not harder scenario. The old brute force way would mean you have to test every single possible combination. In one study looking at epoxy resins, that meant doing 27 different physical experiments. But then you have the Taguchi method. It's a super powerful statistical technique that slashed that number down to just 9 really intelligently chosen tests to find the best result.
And this is where the theory gets real. You make those 9 unique samples, and then each one gets put into a machine just like this for what's called a 3-point bending test. It basically just applies force and bends the material until it snaps, which tells you exactly how tough it is. This physical data is everything.
And here are the exact dials the researchers were turning. They were playing with 3 key things: how long you cure the resin, what temperature you start at, and how much flame retardant you mix in. Each of those 9 experiments used a totally unique combination of these settings.
So after they run the tests, they plot all the data. And this graph, this is beautiful. It shows you just how powerful this method is. You can see at a glance what works best. For curing time, 3 hours is the clear winner. For temperature, the lowest starting temp, 80 degrees, works best. And for the flame retardant, 30% gives you the absolute highest strength. It's all right there.
And just like that, out of only 9 physical tests, we have our answer. No more guessing games. The data gives you a clear, optimized recipe for the strongest material possible with these ingredients. It is a massive, massive leap in efficiency compared to that old brute force way.
Okay, this is where things start to get really futuristic. Cutting your work from 27 tests down to 9 is a huge win. But the next step in manufacturing is asking an even bigger question. What if we could get that number of physical tests all the way down to 0?
So we've seen how the Taguchi method makes physical testing way smarter. But the ultimate goal, the holy grail, is to move beyond the physical world altogether. And that next leap involves creating a perfect virtual copy to do all the heavy lifting for us.
And that brings us to the age of the digital twin. It's pretty much exactly what it sounds like: a super detailed virtual model of a physical thing, or a process, or even an entire factory. And this isn't just some static 3D model. Oh no, it's a living, breathing simulation that's constantly being updated with real-world data. Let's break down how this actually works. Okay, so step 1, it all starts with data. You have sensors all over the factory floor collecting everything: machine temperatures, material properties, pressures, speeds, and all of that information is fed from the real world into the virtual model in real time.
Then in step 2, all that raw data gets put to work. It powers these incredibly sophisticated simulations, and it's used to train machine learning algorithms. This is what gives the digital twin its superpower, its predictive power. It actually learns the behavior of the real-world system, so it can accurately predict what's going to happen next.
And finally, step 3, you deploy it. With the twin up and running, engineers can now run those thousands of tests we were talking about. They can tweak a variable in the virtual world, see what happens, spot potential failures before they occur, and optimize the entire process, all without making a single physical part. And listen, this is not science fiction. This is happening right now. Let's look at a few quick case studies to see how digital twins are completely changing the game in composite manufacturing. Okay, first up, 3D printing with continuous carbon fiber. This is an amazing process that lets you build incredibly strong and complex parts. But if there's even one tiny error in laying down that fiber, it can ruin the whole thing, wasting hours and hours of print time. What is so incredible here is that the system is proactive. A digital twin was monitoring the printer's vibrations in real time. By analyzing that data, it predicted that the printer's belt was about to slip, a failure that would cause a defect. So before it could even happen, the twin automatically adjusted the printer's instructions on the fly to prevent the error. Amazing.
All right, next up, overmolding. This is a process that's used to make lightweight parts for the car industry, and the quality of the bond between the different materials is absolutely critical. We're talking about safety and performance here.
So for this, researchers ran thousands of complex physics simulations to create a gigantic virtual dataset of the entire process. Then, they used all that data to train an AI model that could predict the final bond strength just based on tiny changes in temperature. This created a virtual quality control system that could basically guarantee every single part was perfect.
For our last case study, we're looking at a next-gen recyclable resin called ilium resin. It's being developed for electric vehicle parts, but the chemical reaction that happens when it cures is extremely complex and really sensitive. And the coolest part here is how the digital twin just completely tamed that complexity. It modeled the entire intricate chemical process, and then it used a neural network to constantly check its simulation against real-world data and make corrections. This allowed it to prevent dangerous hotspots from forming while it cured, which could have totally weakened the final part.
So it's pretty clear these virtual prototypes are way more than just fancy models. They are active, powerful tools that are changing the very way we build things. But, getting this technology onto every factory floor, that's not going to happen overnight.
And that's the reality check. There are still some big hurdles to clear. Implementing a full-scale digital twin can be a multi-million-dollar investment. You've got major concerns around data privacy and security. And honestly, just the sheer complexity of modeling these systems is a huge technical challenge all on its own.
But even with those challenges, the potential is just staggering. Think about the journey we just took, from costly physical trial and error to smart statistical methods, and now to infinitely repeatable virtual simulations. We are truly entering a new era of manufacturing. And it leaves us with one last really exciting question. If your entire factory can become a simulation, what's the actual limit to what we can build?